Begin topic 2.2. We are proving parallel lines. So what we're going to deal with today are the converse of the original 2.1 theorems. Remember, the converse is you take your original P implies Q statement and you flip the conclusion and the hypothesis. You do not negate them. If you negate them after you flip them, that becomes a contrapositive. So we're going to do if Q implies P, and we're going to look at our same theorems again. We're going to have two new ones at the end. They're very easy to follow. They don't even have names in class. When you use them, you can call them theorem 2.8, 2.9 if you want, or we can just come up with a name for them, and I'll go back and edit the PowerPoint before I put it on EDSB, and we'll use those names in class. But just remember, we're now on our last class, or in 2.1, we were doing if P then Q. Now we're going to take those same theorems and do if Q then P. So let's look at one real quick. So theorem 2.4, yeah, 2.4, because we stopped at 2.3. This is going to be for group 1 when we do our in-class teaching. And this is converse of the corresponding angle theorem. So we had the corresponding angle theorems in our last lesson. This lesson we're looking at the converse of that theorem. And you'll see it used to say if two lines are parallel, then the two lines in a transversal crossing them creates corresponding angles that are congruent. Now we have if two lines in a transversal form corresponding angles that are congruent, then the lines are parallel. So now we have if Q then P from our last lesson. So let's look at this. We have two lines in a transversal forming corresponding angles that are congruent. So we have line L and M, and then here's our transversal, and we have corresponding angles. Now they're corresponding because they are the corresponding or the same angle created by the transversal on line M and line L. So if we were to shrink this one down and put them on top of each other, we'd be looking at the same angle, and that's what the word corresponding means. So this is going to be a very easy lesson. We really went in depth in 2.1, 2.2. We are already familiar with all this. So simply saying if this transversal creates two corresponding angles that are congruent, and that is given to us to be congruent with the marks, then L and M are parallel. So when you're teaching this in class, you're going to provide examples, and I would like to see a 2-column proof showing that these are congruent. So you can pick angle 1, it's obviously acute, so we can do something like 35 degrees. I don't mind if you pick, I know I always rely on 35 degrees for some reason, and 145 degrees. It's just something that comes out quickly. I know when I ask the class, sometimes you guys will give me 1 degree, and that's fine, because that really shows me that you're listening when I say you cannot do anything by inspection. So when you're, and I'll say this again in class, but when you're preparing your presentation for class, make sure you're giving in the abstract or in general form of the lesson. So that's what we're looking at right now. And then I want you to do something with numbers so that we can see the algebraic support, and that you can actually work through that 2-column proof. 2-column proofs aren't going anywhere. I did say we're going to use them less and less, and this is the last 2-column proof heavy chapter for a while, and we'll appreciate it once we're out of it. Topic 3 doesn't really use them too often, but I want to really make sure we're ready for our final exam, for our midterms, for everything that we're going to be tested on. We really need to know how to use these theorems in a proof. So group 2 is going to do theorem 2.5, which is the converse of the alternate interior angles. So now it's saying if two lines in a transversal form alternate interior angles that are congruent, then the lines are parallel. Alternate interior angles means the alternate part means opposite sides of the transversal. Interior means within or inside of the two parallel lines, or the two lines that we are trying to prove are parallel. So we have angle 1 and angle 2, opposite sides of the transversal. So perfect, we have our alternate angles. They are inside of line L, and they're inside of line L and M, so they're interior angles. So right now we at least know that we can, even if we didn't know any other step, we know that these are on alternate sides of the transversal, and they're both within line L and M. So at least we have a huge hint here by inspection of where we can start this problem. That's really important that we remember the interior and exterior difference, alternate and corresponding. Corresponding, same side of the line, alternate, opposite sides of the transversal. Very important to do that. But again, we have the proof that they're the same measure, so we can look at if two lines in a transversal form alternate interior angles that are congruent, That's our hypothesis. So that's what we're going to draw. We're going to draw two lines with the transversal that form alternate interior angles. So that's exactly our hypothesis. We're not proving that now. We're assuming that this diagram is true. And we have to say that line L is parallel to line M. So the converse for these theorems are much easier to prove in a two-column proof than our stuff in 2.1. So this is actually a little bit easier. It's just now we're adding converse, and we have to make sure we know how to do the converse before we move forward. So let's look at what group 3 is going to be doing. That's theorem 2.6, and that's the converse of the same side interior angles postulate. So these aren't corresponding because they're not the same angle. The corresponding to 60 is up here, and the corresponding to 120 is here. What these are same side. They're on the same side of the transversal, and they're interior angles because they are inside of the two lines that we are looking at to be parallel. We can look at this diagram with the measures, or we can look here. So we have L and M. That's what we're trying to prove are parallel, and our diagram shows our transversal creating angle 1 and 2. So this is just saying, because they're on the same side of the transversal and they're on the interior, we can use the same side interior angles postulate, and those angles must sum to 180 degrees. We've been doing this since topic 1 with no problem. We understood. You guys, I just asked, what is the sum of this? And in every block, everyone right away said, two angles on the same line must sum to 180 degrees. So I'm not going to go too deep into that, but you do need to show me during your presentation, just like in the last theorem when I said you need to show me in abstract. You kind of need to do a two-column proof here, and then I want you to show me the steps algebraically. If you were to pick a number or an angle measure for 1 or 2, I don't mind. We can do 145 or 35, and then just go through the steps and prove to me that they must be congruent, or sorry, supplementary, not congruent. And then this would be a perfect example. I have a 120 degree angle here and a 60 degree angle here. Because these add up to 180 by this theorem, the converse of the same side interior angles postulate, that these two lines are now proven to be parallel. That's why I told you never work from a conjecture if you can work from a postulate or a theorem. Because if you start with a conjecture, that means you have to go back and prove that, and I said this in the last video, before you can move forward with it. So always start with your postulates, start with your theorems, and I'm giving you, in the books, giving you realistically some really good examples of where you want to start. Now, if you forget this on the quiz or test, and you want to play around with it, and you develop something on your own, and it's kind of the proof of this, I'll allow you to use the conjecture, but we really need to know these names and exactly how to apply them. For now, I will be a little bit more lenient, but as the year goes on, we're going to be more and more and more exact in our writing and in our proofs. So go ahead and start developing the strong habits now before you just kind of say, well, I can show through conjecture that this is true, and here's what I'm going to call it, we're going to move forward. So much easier to just break it down. Like I said, same side of the transversal, so it's going to be same side, and they're inside of the parallel line, so it's same side interior angles. All right, let's look at 2.7. This is for group 4. So I wish I hadn't put this up, and we could have just derived the name of the theorem from it. They're very easy theorems if you start looking at the pictures first and then move on to naming them. So this is the converse of the alternate exterior angles theorem. We'll look at the angles. They're on the outside of the parallel lines, so they're obviously exterior angles theorem, and then they are alternate sides of the transversal. So we have alternate exterior, and that's very easy to see here as well as here. They're on alternate sides of the transversal, and they're on the exterior of line L and M, so it's going to be the alternate exterior angles theorem. And again, if two lines in a transversal form alternate exterior angles that are congruent, then the lines are parallel. We did it backwards, and we did it backwards from this in 2.1. We're doing it the converse in this one. Again, it's the converse. We can do the contrapositive to prove that all of 2.1 is true. I know the contrapositive is a little bit trickier when we flip and then negate, and that would actually be a really good quiz question coming up. Is state, if I give you the original alternate exterior angle theorem, state the converse and the contrapositive. Just a little insight into what I'm thinking for your quiz and test. I really want to see that you can break down conditional statements. You can provide an appropriate diagram for our hypothesis or conclusion when it's necessary, depending on if we're using the original, the converse, or the contrapositive. And then I'd like to see some mathematical proof with your 2-column proof in general, and then support it with the mathematical proof. I know it sounds tedious, long, and hard, but the more you practice it, the quicker it becomes, the more efficient you'll become at proofs. And then when you take tests and quizzes and your SAT, ACT, all of that, it's going to be so much quicker and easier. You're going to be able to look at these diagrams, say, all right, angle 1 and 2 are on the outside of L and M, so they're going to be exterior. They're on the opposite sides of the transversal. I know this is the alternate exterior angles theorem. Now, the converse is because I have my hypothesis with the diagram. I'm not proving the diagram. I'm assuming the diagram's true, and my then for the converse is telling me exactly what the outcome of this being true is. So let's move on to 2.8 for group 5. Group 5, this is the first theorem that doesn't have a name. I will admit I understand that group 5 and group 6 realistically do have much easier theorems here to work with, so I really do expect your presentation to be clear, and I'd really like to see some real-world examples. You will have each group will have one laptop, so I would go on Google Maps and show me something, 2 or 3 streets that are parallel to each other. Find something that you can really bring this to life, and where we can see these theorems in the real world. One thing I really like to look at, and if you want to steal it, this is fine, it would be a great example. Think about the windows in the back of my classroom. You have the 2 that are framed. You have 3, and then the center bar in the middle. That's 3 lines that are parallel. But that theorem shows that so you can say if the left side and the right side of the window are parallel, so then the middle also has to be parallel to the other 2 lines. This theorem says if 2 lines are parallel to the same line, then they are parallel to each other. So that's just saying that if my left side of my window and my right side of my window are parallel, and the left side of my window is parallel to the middle of my window in the classroom, then all 3 lines are parallel to each other. Bring up a few really good real-world examples so that you can start thinking about these when you're just walking around. I know you're probably going to say I won't do that, but even if it just once or twice pops into your mind, oh, because those 2 are parallel, this is parallel. You can do it with so many things. When you're coming in from the front doors of the school and you're going up the Meason, we have those 3 rails on the stairs. Those are all parallel to each other. We know the rail on the left is parallel to the rail in the middle, and the rail in the middle is parallel to the rail on the right. All 3 of those are parallel, and if we know 2 are parallel, and then the third one is parallel to one of the other 2, all 3 have to be parallel. There's so many examples of this in the real world that you can see. Why it doesn't have a name, I don't know. We can call it whatever you want, like I said earlier, but just keep in mind, if 2 lines are parallel to the same line, then they are parallel to each other. Alright, and then group 6. Yours is going to be 2.9, and this one, we're not going to do it on the video. We're going to do this one in class. It's part of your. I'm going to keep calling it homework, but realistically, we're flipping everything. We're doing our lessons and notes, which you should be taking notes on all of this. I forgot to put the end. I'm sorry, but in our classroom, when you come in, you're going to be doing what would normally be your homework. That way, you guys can see it as many times as you want on this YouTube video. You can come in the class, you're going to teach one of these theorems, so you should be experts in at least one theorem. And when you're done, I want each group to break up so that there's one expert for every theorem in every group, so that when you're doing the homework, everybody should be able to confidently just take the lead on at least one of the problems that I give. And this one right here, theorem 2.9, is if 2 lines are perpendicular to the same line, then they are parallel to each other. So what that one's saying is if I have 2 lines, let's think of, well, I'm looking at a keyboard right now, and if you look at the keyboard, I have the top line and the bottom line of my keyboard are horizontal. I'm going to draw a really bad keyboard. So my line 1, if I had better control of my pen, and line 2 are parallel to each other on my keyboard, and I'm going to be able to say that by this theorem, because if 2 lines are perpendicular to the same line, then they are parallel. So one thing we always do here we can extend this line in our mind, and that should be much straighter. And we can see that this would create a 90-degree angle if I extended this and I extended this. So we're going to call this red line and this whole side of the keyboard here line 3. I know I joke in class that I'm not the best drawer, and that's why we can't do anything by inspection. I'm gonna admit my lines on this drawing tablet are actually a little bit worse than they are in class. So, but nothing by inspection, everything by what we see on the board, what we see in our problem. Now this is showing you that line 3 is perpendicular to line 1. This symbol is perpendicular. This also is showing you that line 3 is perpendicular to line 2. So by our theorem here, 2.9, if two lines are perpendicular to the same line, then they are parallel to each other. So looking at my keyboard, knowing that they meet at 90-degree angles here and here, that means that line 1 is parallel to line 2. Again, for 2.9, if you're doing 2.9, I really would like to see some more real-world examples. And once you start thinking about looking at things and trying to find out if things are parallel, it is such an easy thing to do. So that's group 6, and so like I said, group 6 and 5, you don't have a lot of proof work to do, but what I want you to do is give us a lot of examples of real-world uses for these theorems, because they don't even have a name. So I would like for you to develop a name that we can use, and then just show me some things in the real world that work. There's so many things that work, and if you have trouble with them, don't be shy. Ask me. I will sit here and talk to you all day about different things that I see that satisfy both theorem 2.8 and 2.9. I'm going to show you the concept summary while I finish talking about some other things we're going to do. So this is going to be our second lesson, where you're teaching the class what you learned from this video, and you're going to be an expert on it. And you had our 2.1 section to kind of get the hang of it and learn what we're doing. So now I expect this to be a much more efficient process. I'd like to see more examples, stronger examples, better understanding, thorough explanations. But don't think that I expect you to be able to answer every question. I am going to be the fifth member of your group, but I'm going to be the silent guy. I'm going to be the guy that you don't want to be in the group with, because I don't say anything. I don't want to contribute. I'm contributing through this video, but if you need help, or if someone asks a question and you're not sure, and I'm going to be the silent member that suddenly is an expert on it, and I will help you. But don't rely on me. Be ready. Make sure you research this enough. You've done enough. Your proofs, your examples are all ready to go on the board, so that you don't have to rely on me. So your participation's coming from these presentations. Don't be scared that if you can't answer a question that someone asks, that you're going to lose participation. As long as each member of your group has a part in the presentation, in the planning, I see everyone working together, your participation grade is going to be fine. If you have any questions, I can publish a rubric for participation, but for right now I want to kind of see how it plays out. Next up is 2.3, and I will actually be teaching that in class on Friday, and I'll probably upload a video for 2.3 sometime this upcoming weekend, since I'll be leading that. We do have our shorter classes on Friday. I don't feel that it's fair in the small amount of time we have to ask you to get in your group, plan out a presentation, and deliver the presentation. I'm going to go ahead and do that on the Fridays for us. And then Monday through Thursday is really going to be for topic 2 especially. I want to see how this works out. I have really high hopes in this. So let's be ready, and keep in mind YouTube tells me how many people viewed the video and for how long. So I kind of have an idea if people are watching the video or not, and I think I'm not too worried about it, but it will show once you're up for presentation whether or not you have a strong grasp of this material.